Okay, so I don't want to spend more time with this introduction. So please, Mr. Suman Acharya, go ahead with the training. If the people will join, I ask you to keep mute unless you have a question. So please, Mr. Suman Acharya, proceed with the training session, and thank you.
Thank you. Thank you, Carlos, for providing this opportunity. So today I'd like to continue from where I had stopped in the previous section. I'll just share my screen. Yeah. So I hope my screen is visible now to everyone.
Yes, yes.
So in the last session, we had done some COMSOL simulation, and as well as MATLAB. I also run MATLAB code for electrothermal actuators. So in last section, I had shown you about structural analysis, eigenfrequency analysis, and also one example on electrostatics. Sorry. So today, that on that day, I had missed one example, which is electromechanical coupling. So let's say when you apply a voltage to a geometry, how it actually deforms. So I'll first like to show you one example in COMSOL. Then after that, I'll run few MATLAB code on various design suspension design, which is a critical part of the accelerometer. Okay, why it is not okay. I'll just I think my cups. So if you have any questions regarding the last session, please you can unmute and ask if you have any doubts or something like that. Yeah. Something came in my screen. Yeah. Sorry, it's taking quite a time. Okay. So if you are new to the COMSOL, so how to start the basic simulation is just go to the file and go to new and model wizard, and it's up to you what type of simulations you want to do, either 3D, 2D, or 2D axisymmetry, and so on. So if you are new, what I always suggest is to perform some 2D example first, because it will save a lot of time. Then once you get the confidence on that, you can move it into the 3D. Also, I like to show some in COMSOL, there is something called application libraries. If you click on files, you'll see the application library. If you click here, there are a lot of examples which you can see here. So if I type accelerometer, so there are few example on accelerometer as well. Or I'm not sure whether. So yeah, there are few example on thermal actuator as well. So you can just open this thing and see the stepwise, like how they had given the boundary condition, and follow the same. If you want to know more about the boundary condition, you can open PDF, which is also available, and then you will get an idea how to perform our COMSOL simulations in this multiphysics tool. So I'll just go to new and go to model wizard. And so since I'm doing electromechanical coupling, so I have to go to electromechanics. So if you just search it here, electromechanics, you will find it here, electromechanics. Since I had already used this one, so it came in my recently used model. So just double click on that and go to stationary. So now right now we are focusing more on stationary solution than any other kind of like transient and other solution. So this is how COMSOL look likes. So first you have to set the geometry, like the dimensions at what scale you want to work, or it's up to you. If you put some meter scale also, you can always play with the dimensions. So uh, for me, I'm like doing putting it into micrometers. So what example I want to show you right now is, I'll just open insert. Okay. So I'll be fixing this point. And sorry for the notation, I'm just using a line to fix, so it will take less time. So let's say if I give a voltage on this bigger length beam, and ground this one to the bottom part of the beam, so how it will deform. Why I'm taking this example is because since the two beam, this one, okay, I'll just change the color. So why I'm taking this example is, once you give the voltage, the blue region will just move down, and there will be a equal uh, gap. I mean, when it get deforms, when it, let's say, comes here, somewhere here, so there will be a like equal gap when it deforms. So it will be helpful in order to visualize as well. So any if I give a voltage on the longer end and ground the shorter end, how it will deform? Any guesses? You can unmute and tell. Okay, okay, we'll see this one in COMSOL then. Okay, so this is the example I want to try right now. So I already set my length unit, which is in micrometer. As I had already told in a previous class as well, if you want to import the geometry, if you have make some geometry in any CAD software, you can import. You have to go to the import section and just go to your geometry where you have saved and just import it. It will take .igs .step and other files which it supports. I'll just delete it for now. So I'll just make a geometry first, rectangle. And then I'll go to the, okay, I'll just make it here. That will be, let's try 50 and 10. I'll make it center. So this is my one of the part. So I'm first making the top part. I'll just duplicate it and change the dimensions. Okay, I'll just take a length 50 as well, and take 2.5. If I make this one, this beam has come, but I want in this end. So you can just check like where it should move by going to the position and just change the value. Since I want to move it on left side, I'll just write -50 because my length is 50, and it will just go to that end, and it will be, I think, height is 5. If I build this one, okay, it went here. So since the length, like width of this beam is 2.5, I think I should minus 1.25. So this is so one of the side I just made. So another end I have to make it again. So I'll just copy, duplicate it. Since another part is another end, so I'll just change the value of x, like positive 50 micron. So it has gone on that side. So I need another part which I'll take as a ground. So I'll just duplicate this one and just uh, move it down. So let's say if I move -10 or -15, yeah. So if I, so there is no gap, I'll just write 15. So here the geometry part is done. Since the medium, the dielectric medium is air, we have to make a bounding box as well. So you just copy or make a duplicate it and make it like, let's say 300 by 200. So this is my air domain. So if you just make the air domain just 2 times or 3 times the actual geometry, it will be fine. You can always check how it is, how your result is changing with different air domain. The total charge at the end boundary should be 0, so you have to consider that. So now once my model is done, I'll go to the materials and just add materials from library. So COMSOL has by default several materials. You can just, oh sorry, so I think in recent materials I already have. So first will be air. So my, if I have selected air, but it came to my all of the design which I don't want part 5. Okay, one thing I missed it, I forgot to union the part. I mean, I'll just go to the boolean and partition and union. Since this one is the single design, so I'll just select this one, and this one. And if you change like so if you click on here, you can see the right tick. If you undo that one, so this one is my first part, second part, and the bounding box. So I went to the part air. My air domain is the bigger box. So bigger box, it has come one here. So you can click and also see, unclick it and click it, will come. After that, I'll select as like silicon for my design. So so this part is silicon and this part is silicon. So far what I have done is I have made a geometry and then I assign a material. Oh, here has also come. Why it is showing this? Oh, I think. Okay. So if you do some mistake, or if you put something wrong in something, the cross sign will come. So we'll figure it out why it is coming later. So after that, since the longer beam will be moving downwards, so we have to define a deforming domain as well. So once you like go to once you select the multiphysics electromechanical coupling, your moving mesh will come, because your air boundary should also like move or displace when your geometry is moving. So go to the deforming domain and click on the air box, which is 1. You can see it here. So you don't need to do anything here, and we don't need this symmetry roller. You just leave it and go to the solid mechanics part. So what we are doing here is we have to fix the part, right? So what I'll quickly do is I'll just go to fix constraint this one, and fix this end and this end. I'll just zoom it, this end. Also, I'll fix this end, because this one I'm like putting as a ground, taking as a ground, so it should be stationary. So I have already, and also you can give out a plane thickness here. Let's say 100. So since if you see here, you should be careful in the dimensions. So if you see here, thickness is in meter. So I want it in micro scale. So here, though I selected in geometry, though I selected in micrometer, in solid mechanics, by default it will come in meter. So you have to change it into micrometer. So what you can do is use a square box and put it U as a micro, it will take as a micro, and meter. So it has come black in color. So our input is correct. So let's say if I remove this one, it won't take. Or let's say if I, sorry, instead of U, if I write F, and or let's say W, what, it is like coming yellow in color, because it is showing unknown unit. So you have to be careful while giving defining a unit as well. So I'm putting now it will take, so it will come black in color. So I have already in solid mechanics part, I have already fixed the part, and you don't need to bother about the air domain. Then you go to electrostatics. Here also, since you have defined distance 100 microns, you define it here the same, outer plane thickness is 100 microns. Then now in electrostatics part, you have to define a voltage and ground the part. So I'll go to terminal. There are two ways of defining voltage, either terminal or electric potential. So right now I'm going to terminal and going to the upper part, and in here in terminal type, I'm giving a voltage, let's say 5. Okay, so here I can just duplicate this one and remove. As a terminal 2, I can define a voltage 0 and select the other part. Or you can just right click here and go to ground, and also like select which one you want to ground, this one, right? Either this one, or you can either select the full or the only one side as well, I mean bottom part. You can just play with COMSOL. You'll get an idea why you have to select what, and why do you have to like define different like terminal electric potential and so on. So I have already defined voltage 0 for my terminal second, and the coupling. So here in solid mechanics, if you see 1, 2, 3, so 1 is my deforming domain, second is my this one upper beam, and third is my stationary part. So in solid mechanics, your air domain is not moving, and just remove this. We don't need that. So if you go to here electromechanical coupling, you can either remove this one or let it be. It's not applicable on that part. So it will be applicable in two parts. So now on the mesh, you go to the mesh. As I had already suggested in last session, please look for different kind of mesh, and what type of mesh you want to do. You have to be careful on mesh section, because it will affect your results. So you can also do a mesh conversion study, and also see the results, how it is changing with different mesh size. So right now I'm just doing fine and build all. So mesh is done. Now I'll go to the stationary part and just run the compute the result. So if you have any question, you can ask me. So here you can see the displacement contour in this part. So if you go to the displacement and surface, right click on surface and go to deformation. See how it will deform. So you can change the scale factor. It's too much, so I'm just changing it. Okay, I'll write 5. Yeah. So this is how it deforms. And so I took this example purposefully because the gap uh, between two plate will be uniform. And let's say in previous lecture by Professor Venkatesh, he had already taught like several things on like different electrostatics, how electromechanical coupling happens, and also pull-in voltage and etc. So let's say I want to see what will be the pull-in voltage in this. So I'll go to the terminal and define, let's say, a voltage 20. Okay, and again I'll run. So let's say I'm not sure at what will be the pull-in voltage. Don't worry about the deformation. I just like took very large scale, so it is deforming like that. I'll just say this one. So again, if I just keep on increasing the voltage, let's say 100, what will happen? Oh, surprisingly, it's working for that also. It's working for 200 as well. Okay, I think the dimension are very, let's say 300. So you can check at what voltage uh, it will crash. So you will get to know the pull-in voltage. It's working for that as well. Okay, 500. It's working for that. So good. Oh, so I think I have taken a very big this thing geometry. So the gap is very large. So I just want to show you the pull-in voltage. So I want to change the gap between this. Okay, I'll just type 12. I have changed the gap now. Now I'll just run the simulation. Yes. So here you got an error. That means, so like in previous example, it was like running successfully. So I think I'll just try smaller voltage because I have changed the gap, and I'll tell you what I'm trying to do. It's working for 300 volt as well. Let's say I'm just trying to do how pull-in voltage works in COMSOL. So don't worry about the voltage. We won't go to that level. Oh, sorry. Yeah. So for this particular design, I'm getting this error. That means uh, the the pull-in voltage will be less than 600 volt. You can do it analytically also. I also have a code for pull-in voltage, MATLAB code, where you can try. I had tried on MATLAB code as well and tried to like match my COMSOL simulation results long back. The code is written by Professor Jiganand Suresh. When I was like working with him, I work on that code. So this is how electromechanical coupling works, and this will be important if you are working on, let's say, accelerometer design, because you have to do a simulation there as well. So it will be necessary. So I thought this will be a very good example to show to you everyone. So if you have any question, you can ask me. Any question regarding this simulation?
Sir.
Yeah.
Sir, what's about contact analysis, sir?
Yes. So you mean what will happen if this one like touches this one?
Yes, yes, sir. It should not go below that, na?
No. It so that I just showed you the example. If I increase the voltage, so there is something called pull-in voltage, right? Which Professor Venkatesh already discussed in previous lecture. So if you keep on increasing the voltage, this one, the top beam will keep on going down, right? So at some
Yes, sir.
point, at at some point, I mean the pull-in happens. I mean this one will completely touch this one. It will get sorted out, right? So your
Mm.
circuit will break. I mean, so if so, the pull-in voltage should be less than 600, so that when I put 600 volt, you got an error. This error, that means that pull-in happened at this voltage. So you have to check till what voltage you can apply on that. So here if you I think if you define I mean that contact will also come if you do not like take this one as ground or something. I had tried that one also. I forgot right now. So this one will touch that one and like try to penetrate this one as well. But
Mm.
I I had taken this one as ground and this one in terminal, and when it will come uh, near to the ground, this one, sorry, I'm just so
The
this
upper
one,
plate should not penetrate the lower one, na,
yes,
sir?
yes, exactly. So that you should be like careful with the voltage you apply, otherwise it will be like short, right? So
Yes. So
yeah.
even I apply the more voltage,
Mm-hmm.
it should stop moving when it touches the lower plate.
Yes, so that it already at voltage, let's say 600, which I gave here in terminal 1, it already touched that one, so that it is not solving. See, you got an error. That is
Mm.
what I am trying to show, and you are like
Okay,
correct.
sir.
Any other doubts? If you have, you can. So this will be important when you are like designing your accelerometer, because you have to do a stationary simulation as well as eigen frequency, and also if you are try to do time dependent or something, it will be helpful. And also when since in, let's say for example, accelerometer, there will be a comb drive as well, right? There will be comb, various different comb, and when your mass is moving, your capacitance will change. So this kind of simulation will be helpful. And also you can okay, I'll just give this one as, let's say, 10 for now, 10 volt, and compute it. So this one has solved. So if you go to the in the results, if you go to the derived value, so let's say you want to see the capacity. This one, this is charge. So if you just copy this one and, oh, what happened to my internet? I'm sure. Charge by voltage is your capacitance. Instead of Q, you write V. So your unit already changed to farad, right? So you should be careful while you can write expression, you can write your formula as well, but you should be careful about the unit. If I do some error here, let's say if I, instead of 1, if I remove this, your unit has gone. So that means your formula is not correct. So you should be like careful about the unit here. So if I write 1, F will come back. So I evaluate that one. If you go to the table here, you can see the capacitance here. So you can sweep the voltage. Let's say I'll just show you that. Uh, instead of voltage 10 here, I'll just write VOL. Okay, let's say VOL, and I'll define this VOL in, since I haven't defined voltage anything called VOL, so it is coming yellow in color. So I just have to go to the parameters, which is at the top, go here and write a name VOL and give, let's say 1, and value. So you can, I already told you, if you write something at a square bracket, it will take as an unit. So VOL is 1 volt, and I already defined it here in the terminal 1 VOL. So if you go to the study 1, right click here and go to parametric sweep and go to plus. So whatever you have defined, those things will come here. And if you see at this one, this start at 1 step, let's say 1 volt, stop at 10. So it will add. So it will do the computation from 1 volt to 10 volt at the interval of 1. So it will calculate for 1 volt, 2 volt till 10 volt. So you can do the parametric sweep and also see the capacitance, how it is changing, how it is varying. So since it will take a longer time, so you can just try of your own and run the simulation. So I want to like stop this one COMSOL now. If you have any doubts on regarding COMSOL simulation and all, you can always contact me, or if you have any doubt right now, you can ask any questions. Okay, I'll just if you want this file, you can share this one as well. For now, I'll just save it somewhere in desktop. Oh no. This one is so. And this one. So next, what I want to discuss about is regarding accelerometer. So we have done electromechanical coupling as well, and also what I like suggest to everyone is you can always put the test structure somewhere. When so let's say this is how like silicon wafer look like, that the geometry. So when you put your devices, there will always a gap, because at the end or the corner you will always find the gap there. You can also like put some structure like test structures. So please approach to the respective people who with whom you are working, and you can put, let's say, parallel plate, cylindrical, and other thing as well. So that way that will give you a very good insight how, let's say, parallel plate actuation, how the capacitance like changes, how it will be measured. So now I'll move to MATLAB. I'll just close everything console and open MATLAB. So before it open here, I just want to go here. So these are few of the accelerometer design which I took from different papers and internet. This is how your accelerometer moves or look like. You'll have a mass, and you'll have a different beams here, which looks like comb like structure, and there you will have a fixed plate, static plate. When it moves, there will be the change in acceleration. Then there will be change in capacitance, which you will be measuring. So I request everyone to go through the papers on different accelerometer. So these are the various design. So this is a like in plane single axis, since it is moving in one direction. If you see see here, it is moving in x as well as y. So this is the another design. I'll don't worry, I'll send the papers regarding the accelerometer as well. So this is one of the design. So this one I took it from Dr. Sambuddha Khan and Professor G.K. Anasure's work. So this is one of the very clever design. And here they had added one different different geometry, which is called DACM, displacement amplifying compliant mechanism. And you can go through the paper, and also instead of having a traditional design, why they put DACM, like extra geometry here. Please try to understand that. It will be very helpful, and I also feel that this is one of the best design so far. They had tried to amplify the capacitance mechanically instead of like electrically, because these are just a beam, and if you amplify it mechanically, you are just amplifying that particular thing. But if you try to amplify something in electrically, you will be amplifying the noise as well. So this is one of the very clever design. And I don't want to work on different, like there are, since it's a very wide topic, I'll just show you the different kind of suspension. Sorry, I'll just go here. If you see the beams here, so this is one type of suspension. It is like holding your entire mass and constraining the movement. Like, I mean, it is like moving in one direction and constraining the other direction movement. So like you have to understand what are like mechanical suspensions. So it is one of the critical component of MEMS sensor, and the mechanical suspension acts like a spring, and like it also helps to constrain the motion in a particular direction. So the design of a mechanical suspension is like all about how to achieve the desired stiffness in different directions. So there are different accelerometer available commercially. They are single pane, and which moves in only either X or Y, or also like it. There are some designs which can sense both in X and Y direction, and also like out of plane motion. So these are few types of suspension. Oh, I forgot to put the name of. These are few types of suspension design, and this is parallel beam suspension, this is folded beam suspension, and this is stator beam suspension. So I just I have a note of this thing, and I can share it with you. Please go through it, and if you have any problem on that, you can always like come with me. I'll like definitely help. So and also, like when you are like designing something, it is always a very always a good idea to do it analytically, then just hit and trial. Because with hit and trial also you'll come up with some design, but it might take a lot of time. But if you do it analytically, you will get a lot of idea how to get a best possible design. So let's say I want to take an example of parallel beam in this session. So what I'll do in MATLAB is, okay, it got stuck here. This is called parallel beam suspension, and the orange in color are all fixed. I'm fixing this end and giving a force here in Y direction. So if you try to move in X direction, it will be very rigid, because this beam won't allow you to move go in a X direction. So my displacement will be always in Y direction. So instead of going to a whole design, first I'll just want to show you the single beam, this one. So I took a single beam, and I'm like applying a force at this end Fy. So E is the Young's modulus, and this is the length, and I is the second moment of inertia, and B is the width of the beam. So why this is important is because the code, MATLAB code, is all about this thing only. So since I'm like focusing only only the like movement in displacement in y direction, and okay, I'm like fixing at this end. Okay. So I'm like fixing at this end and giving a force here. So this is a cantilever beam. So how to like define? I think first I have to show you the MATLAB code. So this is the MATLAB code, how it looks like, and it is written by Professor G.K. Anand Suresh. So this one is like, this code is very handy when you are working on like some, let's say, accelerometer design or any design. It's a 2D beam code. So first there are like FEA beam dot m matcut plot beam lm matcut. You don't need to touch anything here. So if you want to learn more about this, how it works, so there are some comments you can check, and you can, these are the like beam code, how you will define the stiffness K EAL by L. So it might take some time to learn, but once you learn this thing, it will be like this will be very helpful for your design. So you don't need to touch anything on FEM beam, matcut, plot beam, or matcut. So, and you will be running this one, beam.m. So before running the code, you have to make a design. So since I'm like working on cantilever beam, what I'll do is I have to give an input. So before running a simulation, you have to define node file, element file, displacement, and force. Like at what point you are like giving a force. Okay. So I have defined node 1 here at this point, node 2 here, and u1 u2 u3 are, I have defined it here. U1 is the displacement in x direction, U2 displacement y direction, U3 z direction, and similarly U4, E5, U6. Since I'll be like fixing at node 1, that means the value of U1, U2, U3 are all 0. Okay. And this is my element 1, this whole thing. So what I have to do first is I have to write this one first. So I think I have example here. I'll just show you how to run this. Is here. Going should go. Okay, I'll just run this. Yeah. So this is how it deforms cantilever beam. Now I'll show you how to make this one in a beam code. So this is my so I'll share this folder as well, and I have several examples. I'll send it to you as well. You can go each of them and try. This is my main folder, which is beam FEA linear. Go there, you'll find beam, force, FEM beam, matcut, plot beam, ELEM, weight cut. So if you see it, okay, I'll just see the MATLAB code, which I already opened here. So these are the important like files which you you have to like keep it in a same folder. And also you now if you see here note.dat and the coordinates. So here I have to define the uh, length of a beam. So note.dat, if you go to the file and open that folder node, so I have defined 1 2 0 35 0 0. That means this one as well. That means the 1 and 2 are the nodes, node 1 and node 2. 0 and 0 are the like x and y coordinates. So at node 1, since I'm like taking this one as a as a reference, so this one I'm starting from node 1, so my code x and y coordinate will be 0 0. Similarly at the node 2 I have defined x coordinate as 35 and y coordinate as 0. So this is how I like give x and y coordinate. Okay, now node is fine. Now you go to element. Since there is only one element, just a beam, so element, so first row will be element 1 and node 1 and node 2. So node 1 and node 2, okay, 1 and 2, and you will be defining the like breadth and depth of a beam 5 5, and E is the Young's modulus. I'm putting this one in 150 E minus 3 because my code is in micron. So you have to like careful on that as well about the dimension. So I'm like matching the dimension of that. So it's in E3. Okay. So how I'll define here is you go to element. So I have defined the same thing here. After that, I have to fix the constraint. Okay, I have to fix the node 1. So a displacement boundary condition dot that, what I'll do is I'll fix u1 u2 and u3. I mean node 1 in all direction. u1 is x displacement, y u2 is y displacement, u3 is z displacement. I'll fix everything. So if you open displacement dot that, displacement boundary condition dot that, that okay. So node 1 degree of freedom is 1, value is 0. I mean u1 u2 u3. Again node 1, 2 means displacement in y, that is also 0. I guess see this one first is symbol number, and second is node 1 again. DOF is 3, that is the displacement in z direction, again the value is 0. So this helps displacement boundary condition dot that helps us to like putting a constraint on that. Okay, then after that you after that there is one more file which is forces. Just open it. Since it is a cantilever beam, I'm applying a force at the node 2, which is the another end. So how it was like defined here is first is symbol number 1. So I'm applying a force as 2. So 2 means node. DOF, like I'm applying this force on y direction. So I want to deform this beam like this. So this is like displacement at y like degree of freedom is 2, which is in y direction, and the specified value, I mean what is the force I want to apply. Okay, so this is how you define a value or define a geometry. and put it in a single okay, FEM. Here my folder is FEM beam linear. So you have to put every notepad file as well with all of your code. And then you don't not, as I already mentioned, you don't need to touch any other code like code. So if you want to learn more, you can just check it and see how it works. And if so you don't need to see the like do anything at FEA beam code as well, and just go to beam.m. And if you see here how it exactly works, there are some, like, first you load the node.dat, which I put it in a notepad file, made a notepad file and put it. And here see area, how it is like defining E or area, beam width into beam depth, and second moment of inertia formula, and other DOF, and also and this is a scale factor, like how much displacement you want to see, like the geometry, how it displaces. And those are all the things which you can check and work of your own. And if you just run it, so this is how it will define. And you can always, okay, I'll, this one becomes too much, I'll just change the scale factor. Okay, yeah, this is how it will deform. So this is how you can make your own geometry and like define the things. So let's say, for example, so I have done for a, since we have to do for this complicated design, because there are a lot of nodes and elements, I had just shown you a simple beam, cantilever beam, and how you will define that. So far, any doubts, any questions? Okay, if you have no doubts, what I'll do now is, instead of taking one beam, I'll take two beam. I mean this section, this part, and this part, the big probe mass will be very stiff, and I want to like make that one is a stiff here as well. So if you see this file, I'm like fixing it 2 and 1 and 3. And can you tell me how many nodes are here? Nodes is nothing but the discretizing of the geometry. Say, okay. So if you see this one, this beam, downward beam, so this is one single uniform length. So I'm taking this one as a the initial point is a node 1 and end point is a node 2. So this is one of the single uniform beam. So the red one, which is 1, so I'm taking as a whole it's element 1. Let's say if it is not uniform, if they are like different, let's say it's taking time. I don't know what it is. Okay, instead of this one, I'll just go to the saves, put it here. Okay, different color. Okay, instead of this beam, so it looks like this. Let's say first part is orange in color, which is big, and second part is this one. So this is not uniform. So you can't like define the same as a geometry, because you will be defining the coordinates at node file and element file. You will be defining width and depth. So my node will be 3 here, from here to here, from initial points 1 to 2 and 2 to 3. And at element file, I have to define B and D. Like this one, length is, let's say 5x, width is 2x. And similarly for this one, length is something and width will be something. So you should be like careful while defining the geometry. So there are so since this is a uniform uniform length. So this one is element 1, and this one is element 2, and this one is element 3. There are 1, 2, 3, 1, 2, 3, and 4 nodes, 3 elements. And I want to like apply a force. Okay, saves. Force here, let's say at node 2, and I want this one element 2 will be like very, I want to make it very rigid. I don't want to deform that one as well. I want to like make it deform the element 1 and element 3 only, which are two beams in y direction. So I have already defined node dot that file. First coordinate will be 0 and 0. Second will be, let's say, x will be 35 and 0. Third will be this one 0 comma 10, and fourth one will be x coordinate 35 and y coordinate 10. In element file, I have to define breadth and width of the geometry. So I have defined the same. Since I already mentioned element 2, I want to make it very rigid, so I gave a large Young's modulus value here, so it will be rigid. And also I have to fix this one, node 1 and node 3. And if you see the displacement boundary condition that file 1 1 1 1 2 3, it will be all 0. And also node 3 and degree of freedom 1 2 3. I already mentioned 1 is in x direction, displacement in x, 2 is y, and 3 is rotation. So everything will be 0. So that means 1 and 3 are fixed. And I'm like applying a force here at node 2, which I had already defined. And the same thing, you have to do it in your MATLAB file as well. I think I have already file. If I run that one, yeah. So this is how it defines. You can see the black line, dotted line, that is the original design, and red one has shifted little bit. Okay, so this is how you design different kind of suspension in a MATLAB. Now what I'll do is I want to try this design. Say I'll tell you at last why this MATLAB code is more like useful. So for that also I had already made a code, parallel beam file for that, and go to FEMB and paste it here again in the main code and run the simulations. So see, if you see the design of this, since this one is longer in that code, you can always like play with the geometry and make it longer, shorter, or something. I think I'll just make the force, and when you want to increase or decrease the force, you just go to the forces, and instead of giving 4, let's say give 10, and you have to save it again, save it and close it and run the MATLAB code again. I think the scale factor is pretty less, so you are not able to see the actual deformation. So it's moving, but it's still okay. Let me make another 1000. See, this is how it will define. So what as I already mentioned here, what I did is I fixed the end point of a beam, this one, which are in orange color, and I applied a force at the center of the proof mass, so Fy, and apply the force in y direction. So if you are like fixing something, your geometry, which is anchor in MEMS language, so this is how how it will define like deform. So if you see the node file, let's say there are several nodes, 29 nodes. We can count them as well. So if I let's say I want to start it from here, one node, two node till here, then again down three, that will be three. If you want to go this side, this will be four, again five, six. So like that, how many like joints are there? You have to check that one, and you can check the file and like play with the codes. Elements also we are defined. So here this is the Young's modulus, which I already mentioned. So it is 150 E3, which is less stiff, and there are other this thing parts which have the Young's modulus 150 E9. That means that part is very stiff. That means this that part should be proof mass, because we don't want that proof mass dimension is big and it will be very stiff and only your beam will deform. So this is like, this is a very good approach of to design mechanical suspensions and to come with the idea. I have another code as well. Let's say there is something called bandwidth and sensitivity, which is a critical part while designing accelerometer. Okay, so you have to like brush up your fundamentals on that, and I have a code for that as well. I can share it with you, and like you can come with me anytime, so that I'll always help you on that as well. So if you have any doubts on this, you can ask me any questions. Yeah, any doubts? I'll just go here. So what I'll suggest is, like, first it will be very difficult to understand the things. So when I like first saw this code also, like few years back, when I was a like member of IEEE, like you, working on a design of accelerometer or thermal actuator, I also like faced a lot of difficulties. But once you like go through the code line by line, you'll definitely understand everything, and it will be very easier to design. Otherwise, there is like trial and error method also. Like you just go to the COMSOL and change the design, change the geometry, and keep on running the multiple uh, simulation to come with the best design. So it will be like difficult, like if you just follow trial and error method. So I felt this is the best way of like designing a very good suspension design or accelerometer design. If you have any questions, you can ask me, or we can try other example as well if you want any. So, hello, yeah. So what I'll do is, after this session, I'll 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 share a MATLAB code along with a different example, and along with like different type of suspension as well. You can try, and if you want to like design two axis accelerometer, what type of suspension you need, you will also get an idea. Let's say I'll just, okay. Suspension. Okay, I think it's not here. No, it's not there. Somebody asked me previously, how how should one like approach of designing a designing an accelerometer or something. So I have one paper written by Suresh and its student Samudha Khan, Dr. Samudha Khan. I think you had already attended Samudha Khan talk as well. So this is his PhD work, and he has done very came with a very wonderful design. And you can see this paper improving sensitivity and bandwidth of intent capacitive micro accelerometer using compliant mechanism. So which I have told in at the beginning of the lecture. There is something called DSCM. Yeah, it said displacement amplifying compliant mechanism, and how it will increase the sensitivity. So you can see this paper, and also in this paper they had compare other design also, and why their this particular design is the best design at the time. I mean that till the work they had done. So you can check this paper, and there are other extra thing as well. So this is spring mass lever model. You don't need to worry about this. Just go through it. It's a this complete mechanical term. It might be difficult for everyone to understand. So this one will come in compliant mechanism course. You can find it at NPTEL if you are interested. So they have this paper, and also they had done so this is one of the type of a suspension. So why this design is clever is, if I show you this design, this is one of the very clever design, because it can move in either x and y displacement and completely like decouple another direction. What I mean is, if this particular should move in x direction, it will only move in x direction. It will not move in y direction. And if this one move in y direction, there is zero displacement in x direction. So this is something like 2-axis. It can be used as a double axis accelerometer, 2-axis accelerometer as well. So there are like few designs which are like very clever. You can also like come with such a design, and they had like put displacement amplifying compliant mechanism. And I had shown one type of suspension. This one is folded beam suspension. So so you can see here this one. So yeah, go through the papers and try to like go through MATLAB code as well. Then if you have any doubts, you can write a mail to me, and I'll help you on the design part as well. So I like to stop it here. If you want me to do any other example, I'll 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 help you. I can help you on that as well. I have some other things. I think I'll share the notes, and please go through it, and it will be like helpful for you. Yeah. Thank you very much. Uh, Carlos, are you there?
Hi.
Hi.
Yeah.
Yeah, I have finished this one. So if I think they had no any doubts, they can come. I'll share the MATLAB code with the example I have. Then they can go through it, and if they have any doubt, they can come up with me again.
Okay, perfect. So thank you, Mr. Suman, for your kind introduction and all the meaningful explanations. And thank you everyone for being here. So I would like to ask all of you to turn on your screen, please, and say a big thank you to Mr. Suman Acharya. This is his last talk during this MEMS training session, but he will be there. He will be happy to help you in case you have any doubts or you need help. And well, we have our last training session next week, also on Friday, with Professor Venkatesh. So thank you everyone for being here and have a nice weekend. So thank you very much.
Yeah, thank you.
Thank you, Suman.
Yeah, thank you very much.
Bye-bye.
Bye. Thank you.
You will have the recording as soon as possible in the chapter webpage. I will send you a reminder to
Sure.
your emails. Bye-bye.
Yeah, thank you. Bye.